This is the video for Part 1 of Section 1.3, Primes and Unique Factorization. Every non-zero integer n has at least 4 divisors, plus or minus 1 and plus or minus n. An integer which has only these 4 divisors is called a prime. The primes can be viewed as the building blocks of all the integers. So for our formal definition, we say an integer p is prime provided that p is not equal to 0 or plus or minus 1, and the only divisors of p are plus or minus 1 and plus or minus p. An integer other than 0 or plus or minus 1 that is not prime is called composite. So note that the integers 0 and plus or minus 1 are neither prime nor composite. They don't fit into either category. For a quick example, 2 minus 2, 3 minus 3, and 5 minus 5 are all primes. Now, note that in some mathematics courses, primes are assumed to be positive integers. In this course, however, negative integers may be prime. The reason for allowing negative integers to be prime is that later in the course, when studying polynomials, we can use a definition for irreducible polynomials that is a direct analog of the definition of a prime number. We'll see how results for prime numbers have analogs when discussing irreducible polynomials. Note also that since an integer p has the same divisors as minus p, then p is prime if and only if minus p is prime. So our primes come in positive and negative pairs. For one final remark, since the only divisors of a prime q are plus or minus 1 and plus or minus q, if p and q are both prime and p divides q, then p must be equal to plus or minus q. Now in the last section, we saw that in general, a divides bc does not imply a divides b or a divides c. So if an integer a divides a product of two other integers b and c, it doesn't necessarily divide one or the other. Theorem 1.4, however, showed that this result does hold when a is relatively prime to one of the factors b or c in the product. The next theorem shows that this always holds in the case that the divisor is a prime. In fact, an integer is prime if and only if it has the property that when it divides a product, then it must divide one of the factors. So this is Theorem 1.5. For all integers p with p not equal to 0 or plus or minus 1, p is prime if and only if p has the property. For all integers b and c, p divides the product bc implies p divides b or p divides c. To prove this, we'll first write it in this theorem statement in symbolic form. So this has the form for all p is prime if and only if, for all b, for all c, p divides bc implies p divides b or p divides c. Since this is a biconditional statement, then we have to prove two directions. So let's first suppose that p is an arbitrary integer with p not equal to 0 or plus or minus 1. We then have the forward direction. Suppose p is prime, we need to show that p has the property in the theorem. For all b, for all c, p divides bc implies p divides b or p divides c. To prove this, we'll suppose b and c are arbitrary integers. This is a universal statement. Suppose the hypothesis p divides bc. We then need to show the conclusion p divides b or p divides c. To prove this, let's consider the GCD of p and b. The GCD is a positive divisor of p. Since p is prime, then its only divisors are plus or minus 1 and plus or minus p. This implies that the GCD of p and b is either 1, or the GCD is equal to plus or minus p, whichever of plus or minus p is positive. This gives us two cases, and in each case we want to show our conclusion p divides b or p divides c. So for case 1, let's suppose that the GCD of P and B is equal to 1. Since P divides BC and the GCD of P and B is 1, then it follows from Theorem 1.4 that P divides C. Therefore, P divides B or P divides C is true. And this proves case 1. For case 2, we'll suppose that the GCD of P and B is plus or minus P. Since the GCD of P and B is a divisor of B, this implies that P divides B. And therefore, our conclusion P divides B or P divides C is true. And this proves case 2. And this proves the forward direction. For the backward direction, we'll suppose that P has the specified property that for all B for all C, P divides BC implies P divides B or P divides C. We then need to show that P is prime. To show this, we need to show that the only divisors of P are plus or minus 1 and plus or minus P. So let's suppose that D is an arbitrary divisor of P. We need to show that D is either plus or minus 1 or D is plus or minus P. Now, since D is a divisor of P, then there exists an integer r such that P is equal to dr. This implies P divides dr. Now, the hypothesis states that for any integers b and c, if P divides the product bc, then P must divide one or the other, either b or c. We can apply this hypothesis to the integers d and r. And since P divides dr, then P must divide d or P must divide r. This gives us two cases. And in each case, we need to show our conclusion that D is either plus or minus 1 or D is plus or minus P. So for case 1, let's suppose that P divides D. Since P divides D, then there exists an integer k such that D is equal to pk. Substituting this into the equality P is equal to dr, we obtain P is equal to pk quantity times r. And we can rearrange the parentheses to write this as P times kr. And now we have a common factor of P on both sides, so canceling P from both sides of this equality, we obtain kr is equal to 1. Now, since k and r are integers, this implies that k is equal to plus or minus 1, and r must also be plus or minus 1, but we're only interested in k here. And hence, d is equal to pk is equal to plus or minus p, which proves our conclusion. So this proves case 1. Now for case 2, we're going to suppose that P divides R. Now since P divides R, then there exists an integer m such that R is equal to Pm. Substituting this into the equality P is equal to dr, we obtain P is equal to d times Pm, which is P times dm. And again, we have a common factor of P on both sides, so canceling P from both sides, we obtain dm is equal to 1. And since d and m are integers, this implies that d is plus or minus 1, which proves our conclusion. And so this proves case 2. This shows that any divisor d of P must equal either plus or minus 1 or plus or minus P, and thus P is prime. This proves the backward direction, and this completes the proof of the theorem. Now, before we continue, we're going to review mathematical induction. So the property in the theorem can be generalized to products with any number of factors. And to prove this, we can use mathematical induction. Proof by mathematical induction relies upon the principle of mathematical induction, which, like the well-ordering axiom, can be viewed as an axiom of the set of integers. In fact, it can be shown that the well-ordering axiom and the principle of mathematical induction are actually logically equivalent to one another, meaning that each implies the other. So here's the principle of mathematical induction. We suppose P of n is a propositional function with domain the set n of positive integers. Suppose 1, P of 1 is true, and 2, for all k in n, P of k implies P of k plus 1 is true. We can then conclude that for all n in n, P of n is true. Now we can use the principle in this form to obtain the following procedure for proving a statement of the form for all n in n p of n. In order to prove for all n in n p of n is true, we need to prove the two conditions in the principle hold. The first step in any induction proof now is to clearly identify the propositional function p of n and the domain of the variable n. The propositional function may be an equality or a formula involving n, or an inequality involving n, or some other more complicated statement that depends upon n. So here's our procedure for an induction proof for all n p of n, and this is a direct proof. You can also use a proof by contradiction for the induction for the second part of the proof. So first we have what is called the basis step, and for this we need to prove that p of 1 is true. Then second we have the induction step, and for this we prove that for all k in n, p of k implies p of k plus 1 is true. And to prove this, the induction step using a direct proof, we suppose k is an arbitrary positive integer. We suppose that p of k is true, and this assumption is called the induction hypothesis. We then need to show that p of k plus 1 is true. And then using the principle of mathematical induction, we can conclude that for all n in n, p of n is true. Now, this is a direct proof for the induction step. If we use a proof by contradiction, we would apply it to the induction step. Note that when we assume that p of k is true, we are assuming this for some particular fixed integer k, and not for all integers k. We obviously cannot assume that p of k is true for all integers k, since that is what we are trying to prove. Now, the principle of mathematical induction can be used not only to prove statements of the form for all n in n, p of n with domain n, but also statements whose domain is any set of integers of the form for all the set of n and z such that n is greater than or equal to n0 for some n0 and z. In this case, for the basis step, we need to prove that p of n0 is true. We can use induction now to prove our corollary to Theorem 1.5. So this is corollary 1.6. And it states for all positive integers n and for all integers p, a1, a2, down to a sub n, if p is prime and p divides the product a1, a2, down to a sub n, then p divides at least one of the a sub I. So the theorem says that if p is prime and p divides a product of two integers, then p must divide one or the other of the two integers. And so this is extending that result to a product of n integers. So for the proof, we'll use mathematical induction. So we want to prove for all n in n, q of n, where q of n is the propositional function, which is basically the statement in the corollary. So q of n says for all p, for all a1, a2, down to a sub n, if p is prime and p divides the product a1 through a sub n, then p divides one of the a sub I. Okay, now note for the propositional function we're using the letter q instead of p, since p is already appearing in the statement as the prime. Okay, so to prove this using induction, we first have the basis step. So we need to prove q of 1. And so q of 1 will say for all p, for all a1, if p is prime and p divides a1, then p divides a1. Well, since the hypothesis contains the conclusion, then this clearly holds. Next, we have the induction step. So we need to prove for all k in n, q of k implies q of k plus 1. So we suppose k is an arbitrary positive integer. Suppose q of k is true. And we then need to show that q of k plus 1 is true, where q of k plus 1 is for all p, for all a1, a2, down to a sub k plus 1, if p is prime and p divides the product a1, a2, down to ak plus 1, then p divides one of the a sub I. So to prove this, we'll suppose p, a1, a2, down to ak plus 1 are arbitrary integers. We'll suppose our hypothesis that p is prime and p divides the product a1, a2, down to a sub k plus 1. we then need to show that P divides one of the A sub i's. Now the hypothesis is equivalent to P divides the product of the quantity A1, A2 down to A sub k times AK plus 1. So just inserting parentheses around the product of the first k factors on the right of the divides relation, which we can write as P divides BC, where B is A1, A2 down to A sub k, and C is equal to A sub k plus 1. Now the reason for writing it like this is now we have our hypothesis looks like P divides BC, which is what appears in the statement of Theorem 1.5. So since P is prime, then it follows from Theorem 1.5 that P divides B or P divides C. Therefore, P divides A1, A2 down to A sub k, just replacing B with what it equals, or P divides A sub k plus 1. Now by the induction hypothesis Q of k, P divides A1, A2 down to A sub k implies P divides A1 or P divides A2 or all the way down to P divides A sub k. So P divides at least one of the A sub i's from A sub 1 down to A sub k. Combining this with our other result, it then follows that P divides A1 or P divides A2 or all the way down to P divides A sub k or P divides A sub k plus 1. So thus P divides one of the A's, A sub I. And this proves Q of k plus 1, so proves the induction step. And then by the principle of mathematical induction, we can conclude that for all n in n, Q of n is true. Next, we want to review strong mathematical induction. Strong mathematical induction is similar to ordinary mathematical induction in that it is used to prove statements of the form for all n in n P of n, where the domain for the variable n is the set n of positive integers or possibly a subset of n. However, in strong mathematical induction, we strengthen the induction hypothesis. Instead of assuming for the induction hypothesis that P of k is true for one arbitrary positive integer k, we assume that P of I is true for all integers I between 1 and k. Now the method of proof is based upon the principle of complete induction. So the principle of complete induction states, suppose P of n is a propositional function with domain the set n of positive integers. Suppose 1, that P of 1 is true, and 2, for all k in n, P of 1 and P of 2 and all the way down to P of k implies P of k plus 1 is true. Then for all n in n, P of n is true. Now it's not too hard to see that the principle of complete induction implies the principle of mathematical induction. However, it can also be shown that the principle of mathematical induction implies the principle of complete induction. Therefore, the two principles are logically equivalent. Now, the principle of mathematical induction is sometimes called the weak form to distinguish it from the principle of complete induction, which is often called the strong form. Just as we did for the weak form, we can choose the domain for the strong form to be any set of integers of the form the set of n in z such that n is greater than or equal to n0 for some n0 in z. Now it's straightforward to modify the procedures outlined earlier for an induction proof of for all n P of n using the principle of mathematical induction to obtain procedures using the principle of complete induction. So the procedure for a direct proof is as follows. So this is a strong induction proof of for all n in n P of n. So we have the basis step, which is identical to the basis step for weak induction. We need to prove that P of 1 is true. And then second, we have the induction step. And for this, we need to prove for all k in n, P of 1 and P of 2, all the way down to P of k, implies P of k plus 1 is true. In order to prove this statement, we'll suppose k is an arbitrary positive integer. We suppose the hypothesis, P of 1 and P of 2, all the way down to P of k. That is, we're supposing that P of 1, P of 2, all the way down to P of k are all true. This is called the strengthened induction hypothesis. And rather than supposing only that P of k is true, we are supposing that all of P of 1 and P of 2, all the way down to P of k, are true. We then need to show that the conclusion P of k plus 1 is true. And using the principle of complete induction, or the PCI, we can then conclude for all n and n, P of n is true. Now, it's not always easy to decide whether to use the weak form or the strong form of mathematical induction when proving a statement. The usual procedure is to try the weak form first. Sometimes when trying to apply the weak form, we will find that the hypothesis P of k by itself is not strong enough to enable us to conclude P of k plus 1 when we're proving the induction step. Instead, we need to use the hypothesis P of 1 and P of 2 all the way down to P of k. Then we can start over with the strong form.